Section: Introduction. In this section, we discuss the importance of search capabilities in various tasks like reasoning, planning, and navigation. We note that recent studies indicate that transformer-based large language models, LLMs, have difficulties with proof search. It remains unclear if this issue stems from insufficient data, model parameters, or inherent limitations of the transformer design. As LLMs grow in scale, we question whether future models, with more resources, will improve in search and planning tasks. We highlight that techniques like chain-of-thought prompting help LLMs break down search tasks into predicting the next step towards a goal. However, in the worst-case scenario, the model must search during its processing to avoid making mistakes, and we have observed that LLMs can produce errors after taking a wrong turn. To investigate this, we train small transformer models on a basic search task, finding the next vertex in a directed acyclic graph, DAG, from a start to a goal vertex. This task is crucial for many reasoning problems and is similar to proof search in simplified logic. We believe that mastering this task is essential for generalizing to more complex reasoning challenges. Our experiments show that transformers can learn to search effectively when provided with the right training data. We carefully design this training data to eliminate shortcuts or heuristics that could hinder the learning of a robust search algorithm. By generating these examples automatically, we provide the transformer with extensive and ideal training data, allowing us to estimate its maximum potential for learning to search. When the model achieves full accuracy on the training data, it can perform searches correctly in nearly any graph. We aim to identify the algorithm the model learns for the search task and assess whether it relies on learned algorithms or heuristics. Through mechanistic interpretability analysis, we discover that transformers search across all vertices simultaneously, progressively expanding the set of reachable vertices with each layer. This approach enables the model to explore a number of vertices that grows exponentially with the number of layers. However, we find that as the size of the input graph increases, the transformer struggles more with learning the training distribution. Increasing the model size does not seem to help, indicating that simply scaling up the transformer may not enhance its search and planning capabilities. We also explore modified search tasks that allow the model to produce intermediate outputs, similar to chain-of-thought prompting. While this makes it easier to teach the model, it still faces challenges with larger graphs. Our findings suggest that future transformer-based models may not effectively tackle search tasks with standard training methods, indicating a need for alternative training strategies. In the related work section, we review various studies on the search abilities of transformers. While some benchmarks show that LLMs can handle certain graph reasoning tasks, they are generally limited to smaller graphs. Other research indicates that transformers can approximate search algorithms but still exhibit performance gaps, and they often rely on heuristics. We also note that LLMs struggle with real-world graph reasoning tasks and diverse search problems. Despite theoretical findings that suggest transformers can simulate any Turing machine with chain-of-thought, we find that training them to search effectively on larger graphs remains a significant challenge. Section Summary. In this section, we explore the search capabilities of transformer models by training them on a foundational task involving directed acyclic graphs, DAGs, to find paths between vertices. Our findings indicate that while transformers can learn to search effectively with a carefully constructed training distribution, they struggle with larger graphs and may require alternative training approaches to enhance their search and planning abilities. Section: Mechanistic Interpretability. In this section, we explore mechanistic interpretability, focusing on understanding how transformers operate across various tasks. We aim to identify specific circuits or algorithms within the transformer's activations and attention patterns without needing to know the algorithm beforehand. Instead, we reconstruct the computation graph based on these activations and patterns, utilizing a technique called activation patching. Our analysis reveals that large language models, LLMs, engage in shallow searches during their forward pass. We train smaller transformer models on a maze search task, uncovering internal representations of the maze layout. Next, we discuss scaling laws, which are hypotheses supported by empirical evidence regarding how machine learning models behave over time based on their size, data, and computational resources. While we investigate scaling laws across various tasks, we do not include search, reasoning, or planning. We suggest that as models scale, certain abilities may emerge, but we find that this behavior can be explained by carefully chosen metrics. We argue that training loss is a more reliable indicator of model capability, regardless of scale. To assess whether transformers can learn to perform searches, we generate numerous search problems using directed acyclic graphs, DAGs. Each problem consists of a DAG, a starting vertex, and a goal vertex that is reachable from the start. The model's task is to identify the next vertex on the path to the goal. We define the difficulty of a problem by its look-ahead, which is the number of steps the model must take to find the goal. Specifically, for any graph, we consider the path from the start to the goal and the alternative paths that do not overlap with it, determining the look-ahead as the minimum of the path length and the maximum length of the alternative paths. We experiment with three types of DAG search problem distributions: the naive distribution, the balanced distribution, and the star distribution. In the naive distribution, we adapt a random graph model to create DAGs by arranging vertices in a linear order and randomly sampling edges, ensuring no cycles by directing edges to the right. We limit the in-degree of vertices to 4 to keep the graphs less dense, as dense graphs typically have small look-aheads. The balanced distribution is designed to generate graphs with a more uniform look-ahead, allowing us to train and evaluate the model's ability to search multiple steps effectively. We ensure that heuristics are not beneficial for solving the search problems in this distribution. In the star distribution, we arrange vertices in a star shape, with a central start vertex and several spokes leading to the goal vertex at the end of one spoke. For our experiments, we train transformer models similar to GPT-2, using ReLU activation. To aid in mechanistic interpretation, we employ one-hot embeddings for tokens and positional information, concatenating them for the transformer input. Each layer has one attention head, and we maintain the feed-forward dimension equal to the model dimension. Since our input edges are randomly ordered, we allow each token to attend to all others, not just preceding ones, by not using a causal mask. We train a 6-layer model with a hidden dimension of 16, simulating training on a large dataset through streaming training. We continuously sample batches from our generative process, reserving the first few for testing and filtering subsequent batches to avoid overlap with the test set. Throughout our experiments, we utilize the Sophia optimization algorithm with a learning rate of 0.00001, a weight decay of 0.1, and no dropout, using a batch size of 1024 examples. We minimize cross-entropy loss during training, selecting one random path as the ground truth for loss computation, and consider a prediction correct if it lies on any path to the goal during evaluation. Section Summary. In this section, we explore mechanistic interpretability of transformers by reconstructing computation graphs from model activations and attention patterns, revealing that large language models perform shallow searches during reasoning tasks. We also investigate scaling laws and the generation of search problems on directed acyclic graphs, DAGs, to evaluate transformer performance, employing various distributions to ensure a range of look-ahead difficulties while minimizing reliance on heuristics. Section: Sensitivity to Training Distribution. In this section, we explore how the training distribution impacts the transformer's ability to learn a search task. We train 3 models: one on a naive distribution, another on a star distribution where the number of spokes and their lengths are evenly spread, and a third on a balanced distribution where the look-ahead is uniformly distributed, all using an input size of 128 tokens. We then assess each model's accuracy on separate test sets from the naive, star, and balanced distributions across various look-aheads. We find that the model trained on the naive distribution struggles with larger look-aheads, showing low accuracy even for observed values, like a look-ahead of 5. This is because the chance of generating graphs with larger look-aheads decreases significantly with the naive distribution, leading to insufficient examples for the model. The model trained on the star distribution performs decently on balanced distribution examples but not as well on naive ones. In contrast, the model trained on the balanced distribution excels in all test scenarios and can generalize to unseen look-aheads. This indicates that we can effectively train a transformer to perform well on look-aheads seen during training when we use the right distribution. Additionally, the model trained on the balanced distribution with look-aheads up to 12 can generalize to look-aheads of 13 and 14, but not beyond that. Next, we shift our focus to proof search using natural language. We repeat our earlier experiments with a symbolic representation but modify the input to express each edge as a conditional sentence. The task is adjusted to finding the next step in proving a goal proposition based on a starting proposition. This creates a direct link between graph search problems in symbolic form and reasoning tasks in natural language. We observe that the training behavior in this context mirrors that of the graph search setting, with the model facing increasing challenges as the graph size grows, particularly in terms of computational load. We also aim to understand the algorithms that the model learns during training for solving the graph search task. To do this, we develop a method to interpret the model's behavior mechanistically. Our approach involves analyzing the model's actions for specific inputs to reconstruct a computation graph that clarifies its activations, attention patterns, and predictions. Our method includes several steps. First, we compute the activations, attention weights, and output predictions for a given input. Then, we identify significant attention operations in the last layer by perturbing weights and observing changes in predictions. We repeat this for all layers, marking important operations based on their impact on attention weights and output predictions. Next, we explain each important attention operation by identifying the source and target tokens involved and determining which input features are significant for these operations. We test perturbations on both token and position features to see how they affect the model's predictions. Finally, we reconstruct the computation graph by tracing how information flows through the model, ensuring that each attention operation can be explained by the features it relies on. We apply this method to various input examples, resulting in a set of computation graphs that allow us to analyze the model's processing across different inputs. While this method requires multiple forward passes, we successfully apply it to our smaller trained models. Section Summary. In this section, we investigate how different training distributions affect a transformer's performance on graph search tasks, finding that a model trained on a balanced distribution generalizes well across various look-aheads, while those trained on naive or star distributions struggle. We also develop a method to mechanistically interpret the model's behavior by reconstructing computation graphs that reveal how attention operations and input features contribute to the model's predictions. Section: Experiments. In this section, we analyze models trained on a balanced distribution that achieved nearly perfect test accuracy. We propose that the transformer searches all vertices at once, with each vertex's embedding containing information about other vertices reachable within a certain number of steps. At each layer, the attention mechanism takes information from a source vertex at the edge of the current vertex's reachable set, combining the reachable sets of both vertices and updating the current vertex's embedding. This means the reachable set could potentially double in size at each layer. The model might search in either direction, storing either the reachable vertices or the vertices that can reach the current vertex. We illustrate this algorithm visually. To test if the transformer uses this algorithm, we analyze multiple held-out inputs from both naive and balanced distributions, totaling 2,000 inputs. We set specific parameters for our analysis and reconstruct the computation graph of attention operations for each input. We categorize these operations into path merge operations or copy operations from reachable vertices. If an operation doesn't fit either category, we discard it. We consider an input explained by the path merging algorithm if there is a continuous sequence of path merge operations from the start to the goal vertex. Our method effectively identifies the path merging algorithm in trained models but not in untrained models. We gain a detailed understanding of the transformer's computations, counting individual path merge operations and checking if they are maximal, meaning they merge the largest reachable sets available at that layer. We find that the proportion of maximal path merge operations is significantly less than 1, suggesting the model does not learn to perform maximal merges. This is likely because the model is trained on lookaheads that do not align with powers of 2 and has more layers than necessary for the largest lookaheads it encounters. Next, we explore whether scaling helps. We investigate how the ability to search scales with input graph size and model size by conducting 2 sets of experiments, training on larger graphs and training with larger model dimensions. We notice considerable performance variance across different random seeds, so we train models using multiple seeds on balanced distribution examples and measure the minimum loss on a test set from the naive distribution. We set the batch size to 256 due to GPU memory limits. We observe that with a fixed number of layers and hidden size, as the maximum input graph size increases, the likelihood of the model learning the training distribution diminishes. Additionally, the minimum test loss grows as the input graph size increases. To see if larger models can learn to search on larger graphs more easily, we fix the input graph size and train models of various sizes. We find that while larger models can quickly reach a local minimum, there is no clear relationship between model size and the training needed to find the global minimum. We also test decoder-only models with learned token embeddings and rotary positional embeddings, but this does not alter the model's scaling behavior. Section Summary. In this section, we analyze transformer models trained on balanced distributions to understand their search capabilities across graph vertices, hypothesizing that the attention mechanism facilitates the merging of reachable sets. Our experiments reveal that while the models can identify path merge operations, they do not consistently learn maximal operations, and we observe significant challenges in scaling performance with increasing graph sizes and model dimensions. Section. Does in-context exploration, i.e., chain of thought, help? In this section, we explore whether in-context exploration, similar to chain of thought prompting, can aid in learning search tasks with transformers. Although we found that transformers struggle with larger input graphs, we hypothesize that allowing intermediate steps might help. To investigate this, we repeat our previous experiments using 2 prompting methods: depth-first search, DFS, and selection inference. For depth-first search, we create graphs and conduct a DFS from a randomly chosen starting vertex to a goal vertex. We then randomly select a current vertex from the sequence of visited vertices. Each input to the model includes the graph, represented as a list of edges, and the sequence of visited vertices up to the current one. The model's job is to predict the next vertex in the DFS trace. Unlike our earlier tasks where the edges were fixed, here the length of the visited vertex sequence can change. To simplify the model's task, we add padding between the graph and the visited vertices, reserving the rightmost tokens for the visited sequence. We ensure that the graphs we use have a balanced distribution of backtrack distances. In our experiments, we first keep the model size constant at 3 layers while varying the graph size. We observe that the model learns the training distribution across all graph sizes, indicating that a constant number of layers suffices for the DFS task. However, it struggles as the graph size increases. Next, we fix the maximum graph size at 35 vertices and vary the model size. We find that increasing the model size does not make learning easier, although larger models can learn from fewer training examples. Still, the advantage of larger models is offset by their higher training costs. For selection inference, we break down each search step into 2 subtasks: selecting a visited vertex with unvisited children and predicting an unvisited child vertex from the selected vertex. By repeating these steps, we can eventually find the goal vertex. We define 2 variables to create a balanced graph distribution: the frontier size, which counts visited vertices with unvisited children, and the branch count, which counts the child vertices of the current vertex. We generate graphs to ensure that the pair of frontier size and branch count is uniformly distributed. In our experiments, we first fix the model size at 4 layers and vary the graph size. Again, we see that the model struggles with larger graphs. When we fix the maximum graph size at 45 vertices and change the model size, we find that increasing the model scale does not facilitate learning. Overall, we conclude that transformers have difficulty with DFS search and selection inference on larger graphs, and simply scaling up the model does not improve performance.